Okay, so in this video we're going to do some review problems for an exam for a multivariable calculus course. This exam is mostly focused on partial derivatives, max and mins of multivariable functions, directional derivatives, and various topics like that. Okay, so first question here, we want to find a limit. So this is a multivariable limit, and we're doing a limit as xy goes to 0, 0 of the function x squared minus xy cubed over x squared plus y squared. So in two variable functions, limits get more complicated than one variable functions. So we can approach really this origin here along many different paths here. And the question here is that if we approach along, say, this path, really we could go from either direction here, or along this path, from that direction also, you can approach it along many other directions. This path, whoops, different color there, sort of orange path, and you can even do sort of crazier things like, I mean, not that crazy, but like a path like a y equals x squared, or you could curl around, or all sorts of different things. So the limit exists if, one thing is that if the limit exists, all the values along those paths would be equal. So a typical way to show a limit does not exist is to find two paths and show sort of the limit along those paths is not equal to 0. That's what we're going to do here. So first path I'm going to do, common one to check, is x equals 0. So it's like along the y-axis. So if you plug that in, what I get is a limit as just y goes to 0. So if x is already fixed as 0, I just have xy going to 0, 0 means y goes to 0. And then what happens here is you get x squared minus, well, if y is 0, this term on top is 0. On the bottom, you get x squared plus 0 squared, but that's plus 0. Except now I'm noticing something funny. I plugged in y equals 0, and then I said x equals 0. So let's do this again. So limit as y goes to 0, x equals 0. Plug in x equals 0. So that gives me 0 for 0 squared, minus 0 on top. And then I get 0 plus y squared. Well, that is a limit as y goes to 0 of 0 over y squared. But no matter what y is, as long as y is not 0, let's clean that 0 up so it doesn't look like a 6. But as long as y is not 0, this fraction 0 over y squared is just going to be 0. So this is a limit as y goes to 0 of 0, and that's 0. So that's one of the weird things even about one variable limits is we're looking at values of y close to 0, but we ignore when y completely equals 0, or is exactly equal to 0. So that's why this fraction is 0 everywhere. We don't have to worry about the denominator being 0, but it's always 0 otherwise. Okay, next path, let's do y equals 0. It's going to be a horizontal path here. You plug that in, you get a limit as x goes to 0. Now this is the one where you plug in y equals 0. So we get x squared minus, well, when y is 0, we get 0. And then we get x squared plus 0 squared. Now in this case, this is a limit as x goes to 0 of x squared over x squared. So as long as x is not equal to 0 and we don't get that 0 in the denominator, this is really just a limit as x goes to 0 of just 1, which is 1. So what we get here is if we approach along x equals 0, that's the y-axis, we get a limit of 0. If we approach along y equals 0, that's the x-axis, we get a limit of 1. Key thing here is 1 does not equal 0. These were not the same here. And what that means is that the limit does not exist. Because if it did exist, it would have to be both 1 and 0, and it can't be both. So visually what's going on here is here's the graph of this function. And you can see here, like sort of at the origin, the limit doesn't exist when x is 0, y is 0. So it's sort of this funny point here. You've got this sort of break. This is Mathematica trying to graph this. And it looks kind of smooth here, but it actually doesn't work out here. Now to see that, or to show that, you can say, oh, this looks funny, but maybe, you know, it's just a really steep uphill here as you go, and maybe it would work out. So what you can do is you can pick a couple paths. And the two we picked were, one is sort of this ridge on top. You see it better here. There's sort of this top ridge. And the other is effectively this bottom ridge. Now, realistically, what I'm going to do on this question is just plug in x equals 0, y equals 0 as a starting point. If those don't work, you can plug in y equals mx for it. So do a line with any slope m. Or y equals x squared, or all sorts of other things. And here's the picture just to sort of illustrate more closely what's going on. This is along one of the axes. You look at the points along this green line. The function, like everything's 1, and then along the red line, everything is actually 0. So these could like curve around a little bit, but the limits are different. There's this big gap between where the sort of limiting value of these green points and the red points down there. So that means the limit does not exist. Okay. Next one. Here's a limit. Now, this one's going to work out more typically. So this is probably what we should have done with the other one right away. I knew it wasn't going to exist, but how did I know that? Or what did I think to check if that's the case? Well, if you went back up here, if you plugged in 0 for x and 0 for y, you get 0 over 0. And that's not defined. And then I start to think, oh, maybe the limit doesn't exist. Maybe I can do some simplification in this rational function, and maybe I get something that doesn't give me 0 over 0, or I can do something more complicated here. Note that in single variable calculus, if you get 0 over 0, one of the standard techniques to do L'Hopital's rule, but we don't have something like that in multivariable calculus. At least I don't know what to do with that. Okay, so now this one, we're going to do that same thing we probably should have done the start of the next one. We're going to just plug in 0 over 0. And when you do that, you're going to get 0 squared, well, plus minus 0, it's the same thing, over 1. Now it's really the same function with this 1 here. 1 plus 0 plus 0. Well, you get 0 over 1. That means the limit is just 0. So all you need to do is plug in x equals 0, y equals 0. You get a value that you can actually evaluate. You didn't get, say, 0 over 0 or something undefined. That tells me that this is just the value I get, that's the limit. So in this case, that's 0. Now, if you look at a graph of this particular function, here's sort of what things look like. And here we don't have that sort of jump at the origin here. Things are smoothed over here. It looks sort of like a smooth sheet. Whereas the other function in problem 1 here, it's sort of hard to see here maybe, but there's sort of this discontinuity here, this jump, this funniness in the graph, where it's got to be both 1 and 0 at the same time. So that's not the case here. There's some smooth value, which works out to be 0, but it could have worked out to be anything. Okay, next one here. So we're going to do some partial derivatives. So here we have f of xy equals x cubed minus x squared y squared plus 3y. So I'm going to take a partial of f with respect to x. And basically what that means is we're going to differentiate x cubed minus x squared y squared plus 3y, treating y like a constant. So if we do that, x cubed, the derivative is going to be 3x squared. And then we look at x squared y squared. So from the perspective of treating y as a constant, so the partial with respect to x, I get a negative y squared as a constant sort of out in front. And then the derivative of x squared is 2x. Same thing, 3y, there's no x there at all, so that's a constant from x's perspective, or partial with respect to x perspective, so that's a 0. And then this I would tend to write as 3x squared minus 2x y squared, just because I like my x's before my y's here, but that's a sort of stylistic thing. So partial derivative of f with respect to x is this thing. Partial f with respect to y, then x cubed is a constant, so that derivative is 0. And this one we're going to get minus x squared as a constant, and then times derivative of y squared is 2y. And then the derivative of 3y with respect to y is 3. So we end up with negative 2x squared y plus 3. So very similar thing. Now things get a little bit different when we do a mixed partial. So we do two partial derivatives. This 2 means we're taking really two partial derivatives. One is with respect to x, and another with respect to y. Now one of the key things here is you can do this in either order. You can either take the partial with respect to x first and then the partial with respect to y, or the partial with y first and then the partial with respect to x. So what you need to do is pick one of these two that you have. So let's take this first one, and I already did a partial with respect to x, so I need to do partial with respect to y of 3x squared minus 2xy squared. Here. And so then when I do that, derivative of 3x squared with respect to y is 0. I'll get a negative 2x times the derivative of 2y, or sorry, derivative of y squared is 2y, give me negative 4xy, and that's my answer. So you could stop there. Now, I made an arbitrary choice here, which was to start with the partial of f with respect to x, and then take a partial of that with respect to y. You could have started with this partial f with respect to y, and done a partial with respect to x. So if you did that, what you'd get here is negative 2y is the constant part with respect to x, and then the derivative of x squared is 2x, derivative of 3 is 0, you would get negative 4xy there as well. So this is the key thing. As long as our function is sufficiently nice, which this is a polynomial, that's going to work out. Here there's some technical sort of definitions you could put there. These two mixed partials should be equal. And so you can do them either way. You don't have to do both of these to solve the question. You can do either one. Same thing when we do here D. We're doing 3 derivatives, 2 with respect to x and one with respect to y. And you can do these in either order. Probably the easiest thing to do here is I've already got derivative with respect to x and y. So to get down here, I just need to take one more derivative with respect to x. So probably the simplest thing is to take a partial with respect to x of our answer to C, which is negative 4xy. And that's just x times the constant negative 4y here. So that's just negative 4y. Now you could have done this in other ways. You could have taken your partial, let's say, how about with respect to x twice and then with respect to y? So this was your partial with respect to x was up here. So you could have done a partial with respect to y of the partial with respect to x of the partial with respect to x. If you did that, you'd get a partial with respect to y of, okay, partial with respect to x is going to be 6x minus 2y squared. And then I take a partial with respect to y of this. 6x is 0 for y's perspective. Derivative is 0 from y's perspective. And I get a negative 2 times 2y. That would give me the negative 4y as well. So now since there's 3 orders you can do this in, just pick whether you're taking y first, second, or third. But they all should give you the same value. So here you've already got 2, so it made sense to use the simplest one first. Or use the one you already have. And just take one more derivative. Okay. Next one here. We want to find an equation for the tangent plane to relieve the graph of z equals 2x squared minus 3y cubed plus xy at the point 1, negative 1, 5. So what we're going to do here, little concern here. So this one, actually I'm not sure if this makes sense. So let's work through this. So it should be the case that 1, negative 1, 5 is a point on this graph. Otherwise this whole question doesn't make sense, because I'm trying to find a tangent plane to a surface at a point that's not on the surface. I think this might actually be a typo, but let's see, maybe I'm wrong. So I do 2, I'm going to plug in 2 times 1 squared minus 3 times negative 1 cubed plus 1 times negative 1. Well, if you do that, you're going to get 2 plus 3 minus 1. That should be a 4. So this 5 should be a 4 to make this problem work. So let's just change that to a 4 and do this in a way that would make sense. Clearly something's wrong here because the point 1, negative 1, 5 is not on the surface, and thus the tangent plane question does not make sense. But you could change this here. That should not happen on an exam, but sometimes it does here, and then you just sort of ask, hey, what did you actually mean? Okay, so what we're going to do now, let's find a tangent plane to z equals 2x squared minus 3y cubed plus xy at the point 1, negative 1, 4. So to do this, there's a formula. That formula, one way to write it is z equals z naught plus the partial of f with respect to x at x naught y naught times x minus x naught plus the partial of f with respect to y evaluated at x naught y naught times y minus y naught. So here our point here in our case, that's x naught y naught z naught. That should be 1, negative 1, 4 here. And f of xy would be the 2x squared, this thing here, minus 3y cubed plus xy. So that would be the two things. And then you just evaluate these things here. So what you would get here, let's see, partial f with respect to x see, that's going to be 4x, nothing from there, plus y. And so the partial of f with respect to x evaluated at x naught, y naught, I'm going to plug in 1 for x in this function and negative 1 for y. So that's 4 times 1 minus 1. That's 4 minus 1, that's 3. And then I do my partials with respect to y. So I take this with respect to y. I'm going to get negative 9y squared plus x. And then I need to evaluate that at x naught, y naught, which is, again, x is 1, y is negative 1. So you get negative 9 times 1 squared, which is 1. Sorry, actually, negative 1 squared. So y squared is also 1, though. Plus 1 for the x. So that's negative 9 plus 1, that's negative 8. And so my tangent plane is z equals, z naught is 4, plus 3 times x minus x naught is 1, minus 8 times, so plus the partial with respect to y, that's the negative 8, times y minus negative 1, but that's plus 1. There. So this would be one version of the tangent plane. You could simplify this down and say z equals, let's see, we'd get 3x, let's just expand it out here, 4 plus 3x minus 3, minus 8y minus 8 here. And so that would give us, let's see, z equals, whoops, around here, do this. So that would give us z equals, let's see, 3x minus 8y, and then we have a plus 4, minus 3 is 1, minus 8, minus 7. So that'd be a relatively nice form of the tangent plane. Technically, I guess you probably could have stopped here, said, oh, that is an equation of the tangent plane. That'd work out. Another way you might do this question, here, so sort of a very different, maybe somewhat different feel, is I'm going to think of this plane, not really what I did is I treated this surface as a function here, z equals some function of x and y. You could also view this as a level curve of a function of 3 variables. So what that would look like, let me pick a, oh, that'll be fine. So what that would look like is you take this equation and you would say, like, let's make a, how about a capital F, x, y, z, and say that's, hopefully equals there. Say what that is it's 2x squared minus 3y cubed plus xy, but then minus z. So I'm taking this z and moving this over here, and then what I get is that this equation is really the set of points where f, capital F of x, y, z equals some constant, in this case 0. So this is a little bit different setup here. And when you have that, what you can do is your normal vector for your tangent plane is actually the gradient of f evaluated at x naught, y naught, z naught here. So you've got a point on your plane here, and then a normal vector here to your plane. And this is really just a result that says normal vectors are orthogonal to level surfaces, and because this is a constant, that makes the points that satisfy this equation a level surface for this capital F of x, y, z, and so its gradient should be perpendicular, or the gradient of capital F should be perpendicular at that point. And so the gradient, let's just do gradient of f here, well, that's the vector of the partial derivatives. So with respect to x of this function, you get 4x, nothing from that, we get a plus y, nothing from the z. From the y, you get a negative 9y squared plus x, nothing from the z. From the z, you just get this negative 1. So if you do that, well, let's just say that let's do this. So at x naught, y naught, z naught, that was 1, negative 1, 4. So let's see, that'd be 4 plus y plus negative 1, that's 3. Let's see, negative 9 times negative 1 squared, that's negative 9, plus 1, that's negative 8, and then negative 1. Note, this 3 and that negative 8 match this 3, that negative 8. They were calculated exactly the same way here. but then we have a normal vector, and so our plane should be 3 times x minus x naught, that would be 1, plus negative 8, which is really minus 8, times y minus y naught, which is y minus negative 1 is y plus 1, plus negative 1, which is really minus 1, times z minus z naught, which is 4, equals 0. So you could do that, and if you simplified this down, you would get 3x minus 8y minus z equals something. Let's see, you would get a negative 3, a negative 8 would be minus 11, and then a plus 4 would be a minus 7, but that was on the other side, so that'll turn into a 7. Instead of trying to distribute this and figure that 7 out, one thing I like to do is plug in my point, 1, negative 1, 4. I just say it's 3 times negative 8 times negative 1 is plus 8, that's 11, minus 4, that's 7. So this equation has to be true for all the points, in particular for 1, negative 1, 4. So just plug in those for x, y, z once you have that normal vector, and you can figure out that right-hand side. Note, this is the same equation here. Well, it's equivalent equation. What we've got over here is like we move the z to the other side and the 7 over here, and that matches what we had before. So two somewhat different methods, sort of the same here, but a little bit different. Okay, next one. We have z equals x squared y plus natural log of y, and we want to find the differential of z. So the differential of z, all that is when you have dz, this is going to be a partial z in the setup of with respect to x times dx, plus a partial z with respect to y times dy. Now, this I think is sometimes a little bit confusing because it's almost too easy. So what we're going to do is dz here. That's a partial z with respect to x. So I'm going to take this z is x squared y plus natural log y, and I'm going to differentiate with respect to x. That's going to give me a 2xy from the x squared y, natural log y, that's 0. And I'm just going to put that in, well, I don't need parentheses in this case, but then I'm just going to multiply that by dx. I'm going to do nothing with the dx. I'm just going to leave that as part of my answer. Partial of z with respect to y, see this first term is going to differentiate to x squared, and then I'll get a derivative of natural log y is plus 1 over y. Here I need my parentheses. And then I'm just going to leave the dy. And that's it. That's my answer. So I think there's a temptation to like try and do something with the dx or the dy, but no, this is the differential here. And what we're saying here is that if you did a tangent plane or a linear approximation to z equals x squared y plus natural log y at some point, is that if you change x by a little bit and y by a little bit, you can use these sort of coefficients based on the point you're at to figure out how much z changes by. So we're going to do that in part B here. So we're going to use this linear approximation to estimate the value of z when xy equals 3.01, 0.98. And the whole goal here is to do this without a calculator. Now I trust you can just plug in these values in a calculator and get a number out. But that's sort of we want to think about what can you do without a calculator, or if you had like this is part of some, say, big computer program where you're trying to do this billions of times, it might be too slow to calculate, say, that natural log over and over, and you just want to get a quicker thing and be able to say, oh, this is about right, and maybe it's good enough. So again, I'm just going to write down the function we had. Z equals x squared y plus natural log y. I'm doing that from memory. Let me make sure that's right. Yep. Here. And what we had was we had this dz here. So when we look at this, what I look at is xy here. This is 3 plus 0.01. And then the y is 1 minus 0.02. So the point here is if I plug in x is 3 and y is 1, so 4, x equals 3, y equals 1, put an arrow here. What I get is z is 3 squared times 1 plus natural log of 1, which is 9 here. Natural log of 1 is 0. That's just 9. So I can do that by hand. Calculate 9 here. So I expect that 3.01, 0.098, when x is 3.01, when y is 0.98, I can find z to be something like 9, but we can do better than that. And so to do better than that, what we're going to do is we're actually going to calculate this differential, dz. So that's going to be 2 times our x is 3, our y is 1, but then this dx, that's going to be how much we changed x by. So that's 0.01. So that's like the change in x. And then we get x squared plus 1 over y. So that's 3 squared plus 1 over 1. And then the dy is how much we changed y by, or how much we added to y, which is a negative 0.02. And now we can calculate this out. We get 6 times 0.01, 0.06, plus this is a 9 plus 1, that's 10 times negative 0.02, that's minus 0.2. So this is negative 0.14. So what we're saying here essentially is that if we use the tangent plane approximation or a linear approximation to our z, when we have z equals x squared y plus natural log y, and you approximate that, if you move from 3, 1 and you add 0.01 to x and you subtract 0.02 from y, we can use this differential formula to figure out that means z, we would add 0.14, which is really subtract 0.14. So what we suspect here is we get the value of z, we approximate z, it should be the 9 that it started at 3, 1, minus 0.14. And that should be 8.86 here. So that's really our answer here. And I didn't really write out my linear approximation. I mean, I used the differential, which is really the same thing. So if you wanted to have the linear approximation here, so if you wanted to do linear approximation, x and y, or something like that, what you would do is you'd say it started at 9, and then I add 2 times 3 plus 1. That's 6 times x minus 3. So x minus 3 would be the 0.01 here. Plus 3 squared with 9 plus 1, that's 10, times y minus 1. So this y minus 1, that's like the negative 0.02. I think this is a little bit unnecessary here at this point, but you could go through with this and then calculate, if you wanted to, you could calculate really this formula here. So the 9 is there. Let's just do this. So L of then 3.01, 0.98. This is 9 plus 6. X minus 3, that's the 0.01. So the 6 times 0.01, that's the 0.06. 10 times y minus 1 is negative 0.02. The 10 times negative 0.02, that's the minus 0.2. And we're sort of just adding those two to 9. 9 plus 0.06 minus 0.2. And if you add these up, let's see, 9 minus 0.2 is 8.8, and then we add 0.6, you'd get the 8.86. It's the same thing. Just do you really want to write down the linearization or not? Or maybe it makes you understand what the linearization is. Another thing I would do here, let's check how close we were. So this was x squared y, so that's 3.01 squared, times y is 0.98, and we're supposed to add to this the natural log of y. So that was our sort of equation here. It's x squared y plus natural log of y. And the question is, do we get something close to 8.86? Certainly closer to 8.86 than to 9 here. And what we get is 8.8, well, it would round to 8.86, but, you know, a little more precision there. So we can approximate this value to a lot better degree than just saying 9 here if we use the linear approximation. Okay, next one. So we want to say let f of xy be x squared y minus 8x cosine y, and then x is 3 cos t, y is 2 sine t, and then we're going to find a derivative of f with respect to t, really when t equals 0. Now, notationally, there's a little bit of confusion here. F is given to us as a function of x and y, but we're taking derivatives with respect to t. Now that's a little bit weird, but x and y are both functions of t, so in some sense I could write this f as f of x of t, comma y of t, and maybe say this whole thing is, I don't know, like a capital G of t or something here, and say this is really the derivative of g with respect to t. But you'll often see this notation, here's the derivative of f with respect to t, where it's understood that this is a composition of functions. So what we're going to do here, we're going to use the chain rule, because we have a composition, and the setup here is that df dt, what we need to do is you take partial of f with respect to x, and then you have to multiply that by dx dt. So I always think in my head like these dx's should cancel, give me df dt, but I need one of these terms for each of the variables that go into f, sort of these intermediate variables. So I need a partial f with respect to y times a dy dt. Again, I think the dy should cancel. And now I'm just going to take these derivatives and partial derivatives. Partial f with respect to x, that's 2xy minus 8 cosine y. Derivative of x with respect to t is going to be negative 3 sine t, plus partial f with respect to y is going to be x squared plus 8x sine y. Derivative of cosine y is negative. Sine y is going to turn that negative to a positive. And then the derivative of y with respect to t is going to be 2 cosine t. So you get this formula here. There's a temptation to go ahead and plug in 3 cosine t for x and 2 sine t for y. That's going to generally create a mess. What's easier to do, well, not that bad. You presumably could work through that and then plug in t equals 0. What's easier to do is say, I'm going to plug in t equals 0, but when t equals 0, x is 3 times 1, that's 3, and y is 2 times 0, that's 0. So I can plug t equals 0 into my formula for x and into my formula for y, and that gives me sort of values I can just plug in at this level here without having to substitute in and make this whole thing in terms of t. So when I do that, I'm going to get 2 times 3 times 0, note that times 0 makes it 0, minus 8 cosine of 0, that's 1, and then I get minus 3 sine of 0, well that's 0. So if I was smart about this and looked ahead, I could have seen that sine of 0 is 0, so this whole term doesn't matter. I could have even avoided finding this partial of f with respect to x if I noticed that right away. This one here, let's see, x is 3, so I get 3 squared plus 8 times 3 is 24, but then sine of 0 is 0. And then I get 2 times cosine of 0 is 1. So what I end up with is this whole term goes to 0 because of that 0. 3 squared, 24 times 0 is 0, so I end up with 9 times 2. So my answer should be 18. Okay, next one. More partial derivatives. Now we have a function of, so g is a function of x and y. It's this thing here, xy squared minus x natural log x. But then x is a function of both s and t. So our intermediate values, instead of just having a t, there's an s and t. Now, what that means here is I can't take a derivative of g straight up. I have to do a partial derivative of g with respect to s or with respect to t. So when we do this with respect to s, what you get is really it's the same thing as before. You get a partial of g with respect to x times, now not derivative of x with respect to x because x has 2 variables, so we do partial x with respect to s. Again, if I cancel these dx's, I get partial g with respect to s. It's not a correct step to cancel them, but it'll help you remember what to do. And I have to add another one for one of these dy's. You get a partial, or another one for y, partial g with respect to y, times partial y with respect to s. And then at this point we have s is 1, t is negative 2, and then what are x and y? So x is s plus 2t, so that's 1 minus 4, x is negative 3. Y is e to the t minus s, that's e to the negative 3. So we're going to get an answer with some e's in it, presumably. Maybe not, maybe they'll all cancel out, but could be. Okay, so now partial g with respect to x. Oh, I wrote those down. I didn't actually calculate my partials here yet. Partial g with respect to x, that's going to be y squared minus natural log of y, times partial x with respect to s, that's 1. Okay. So plus partial g with respect to y, it's going to give me a 2xy, minus x times 1 over y, that'd be like x over y, might be a way I'd write that. And then we have to multiply partial of y with respect to s. So that's going to be a negative e to the t minus s. Okay. So now when we plug these values for s, t, x, and y in, what I get is y squared That's e to the negative 6. That's going to double the exponent to square. Minus natural log of y. Well, natural log of e to the negative 3 is just negative 3. So minus negative 3 times 1 doesn't change anything. Plus 2xy. So that's 2 times negative 3 times e to the negative 3. Minus, this is really x over y. So this is negative 3 over e to the negative 3. We should probably do some work on this. So this is, whoops, e to the negative 6 plus 3 plus, okay, I'm going to get a minus, well, let's do the plus. Here, minus 6 e to the negative 3. Clean that up there. Minus 6 e to the negative 3. And minus cancel. I'll get 3. That e to the negative 3 in the bottom becomes a plus 3 e to the 3 on top. And when I look at this, what I get is I have a 3. I have an e to the negative 6. How about let's do 3 plus 3 e to the 3, maybe highest exponent first, plus e to the negative 6 minus 6 e to the negative 3. You get something like this. So you could turn that into a decimal if you wanted to. Next one, partial g with respect to t. When s is 1, t is negative 2. Now if we look up here, let's see if we can get this to line up right. S is 1, t is negative 2. Same value of s and t. We can reuse the s, t, x, and y that we had. And so then we just need to use our chain rule, which is dg dt. This should be a partial of g with respect to x times partial x with respect to t plus partial of g with respect to y times partial of y with respect to t. And so what we get, let's see, I'm going to write this here just so I can see what's going on here. Partial g with respect to x. Well, it's really this y squared minus natural log y again. But then partial x with respect to t, this 1 is going to get replaced by 2. Partial of x with respect to t is 2. Plus, I can reuse my partial of g with respect to y. So it'd be 2xy minus x over y. And then partial y with respect to t, well, I'm going to get a positive out here. So instead of a negative e t to the negative 3, and now I'm looking at this, and I'm worried that I actually left this off on my previous answer. I'm going to write this here as e times t to the minus s here. And now I'm looking at that. It's probably a good thing I went back and did this, because now I look at this, and what I see here is that I end up with, let's see, this was partial g with respect to x, partial with respect to s. So this line is right here. Here I did this y squared minus natural log y times 1. Here I did 2xy minus x over y, but then I left off my negative e to the t minus s. So what I should have done, I have to erase all this here. So we can get rid of all of this stuff. Totally wrong. I should have had a, let's see, left off negative e to the negative t minus s, so that's a negative e to the negative 3 here. And so what I get, let's see, this is e to the negative 6 plus 3. Let's see, I get a, when I distribute this e to the negative 3, I'm going to get a minus 6 here. And e to the negative 3 times e to the negative 3 is e to the negative 6. But then that negative is going to turn that into a plus. And then the other term, we get negative, negative, negative. That's negative. These e to the negative 3's will cancel. I'll just get a minus 3. So the minus 3's cancel, and it looks like when I'm done, I get 7e to the negative 6, which is 7 over e to the 6. So a nicer answer here, and before I just left this off because, I don't know, just missed it for some reason. Had it right here and just didn't write it down. Okay, do the same thing here. S is 1, t is negative 2, and there's our x and y here. I want to keep those in view. And so what we get, let's see, y squared minus natural log y. Well, I can copy that value from here. I could reevaluate it, though. E to the negative 6 plus 3. Now 2, I get a 2 there. 2xy minus x over y. Same thing as here. So that's going to be a negative 6 e to the negative 3 plus 3 over e to the negative 3. Kind of simplify this as I go through. And then my e to the t minus s, that's going to be an e to the negative 3. I don't get a negative like I did up here. And so what that gives me, let's see, I distribute here, I get 2 e to the negative 6 plus 6. I distribute here, the e to the negative 3 times e to the negative 3 is e to the negative 6. So minus 6 e to the negative 6. E to the negative 3's cancel. I get plus 3. And this one I have 3 plus 6 is 9. And then I get minus 4 e to the negative 6. You could write that if you want as 9 minus 4 over e to the 6. So there's your answer there. Next one. Do this one without making little mistakes like that. Let's see. So we want to find the directional derivative of f of xy is 3x times e to the y plus 4xy at our point 1, 0 in the direction of this vector. So our directional derivative in the direction of, now if this is a unit vector of f, what this is you take the unit vector dotted with the gradient of f, and then you can evaluate that at the point here. So to do this, I have to change 3, 1 into a unit vector. So my unit vector, that's going to be 3, 1. I want to get a vector in that direction, but a unit vector in that direction. So I divide by the magnitude of 3, 1. So this is 3, 1 over the square root of 3 squared plus 1 squared. This is 3, 1 over the square root of 10. And I'm just going to leave this like that. You could write this, well, let me just write it out, as 3 over square root of 10, 1 over square root of 10. But it's going to turn out when I do this dot product, it's probably simpler to deal with the square root of 10 at the end here. So what I'm going to get now is I'm going to get u, and so that's 3, 1 over square root 10, dotted with gradient of f. So I'm going to take a vector dotted with a vector. And this gradient of f is just a vector of the partial derivatives. So with respect to x, I get 3 e to the y plus 4y. So the first component of the vector is the partial of f with respect to x. Second component of the vector is the partial of f with respect to y. So it's going to be 3x, derivative of e to the y is e to the y, plus 4x. So I'm going to dot these two vectors. Now, because I only care about this at the point when x is 1, y is 0, I'm going to plug those in right now. So a couple things. I can have a 1 over square root of 10, 3, 1. I can sort of move that scalar out there. That's why I didn't convert this into here, because I sort of saw that would be a nice thing to do. Presumably in the future makes the dot product calculation a little easier to think about. Now I plug in x is 1, y is 0. So e to the 0 is 0. 3 plus 0, that's just 3. Let's see, x is 1, y is 0. That's 3 plus 4. And then that's 1 over square root 10 times 3, 1 dotted with 3, 7. So this is 1 over square root 10 times 3 is 9. 1 times 7 is 7. So we get 16 over the square root of 10, which, I don't know, you could leave like that. It's probably just fine. If you wanted to continue on, you could say this is 16 times square root of 10 over square root of 10 times square root of 10. And then you would get 16 times square root of 10 over 10. And then you could cancel a 2 and get 8 square root of 10 over 5. So these should give you the same decimal. It's a question of what are you going to do with this as to do you want to simplify. Next up. The tangent plane equation. We did one of these earlier, but it was z equals some function of x and y. Here, z is really defined implicitly. I guess you could solve this for z. We can say, consider the surface defined by x cubed yz plus 3x squared equals 5 minus y squared. We want to find an equation for the tangent plane to the surface at the point 2, negative 1, 1. Okay, so let's plug in this point and make sure it's on the surface. That didn't work out with the last one, so first thing here, just check the point. You're going to get 8 for x cubed times negative 1 for y. Z is going to be 1, that won't matter, plus 3 times x squared, that's 2 squared is 4. So let's see, this is negative 8 plus 12, that's 4. And then 5 minus y squared, negative 1, that's 4. Hey, this actually works out. Okay, so you don't really need, you should be able to assume that's correct, but because I messed up the other one, I want to make sure that was correct here. Okay, leave that there. Now what I'm going to do here is I'm going to define a function of x, y, and z. And what I want to do is make the points that satisfy this equation here that we're looking at, make those be a level surface. So what I'm going to do, I'm going to say this is x cubed yz plus 3x squared, so I'm going to get the left-hand side, but I'm going to move the y squared to the other side. Now, if you do that, then this equation, so this x cubed yz plus 3x squared equals 5 minus y squared, that's really the same thing, completely equivalent to f of xyz equals 5. Now, you might see some people who really want to have a 0 here. For what we're going to do, the fact that that's a constant is all that matters. If you needed to have the 0 there, what you would do is you could just add a minus 5 here, and then you could get sort of minus, well, this would be 0 then. So I'm not going to do that here, but it'd be a way to fix this up if you wanted to make that 0. Okay, so now what we're going to do, if you have a level surface, the gradient vector is normal to the level surface. So the gradient of f, again, it's a vector of partial derivatives. So here's our f x, y, z. I'm going to take a partial with respect to x. That's 3x squared yz. Let's make that a nicer z. And then plus 6x. And then I take a partial with respect to y. Gives me x cubed z from this term. That term's a constant for y. And then I get 2y. And then a partial with respect to z just gives me x cubed y. So I get that gradient. And then I really want to evaluate this gradient at our point 2, negative 1, 1. And so that's going to give me 3 times 2 squared, that's 12. And then I'll get a negative 12. 6 times x, that's 12, so that's 0. That's nice. Let's see, 8, 2 cubed is 8, so I'm going to get 8 minus 2. And I get 8 times negative 1, that's negative 8. When I get done, I get 0, 6, negative 8. So this is our normal vector to our plane, and so that's really our normal vector to the plane. And then what I would really do with this, to be honest, I would say this is 6y minus 8z equals some constant. That's our tangent plane. Note, I don't have an x term because I had a 0 here. And to figure this out here, what I'm going to do is I'm going to plug in x, 2 for x, negative 1 for y, 1 for z. So I'm going to look at 6 times negative 1 minus 8 times 1. See, that's negative 14. So negative 14 has to go there. And in some sense, I'm done. Now, you'll notice here, well, you may notice that these coefficients all are even. So this is equivalent to, you could divide both sides by 2, get 3y minus 4z equals negative 7. So it'd be a nicer looking answer, easier to work with. That's basically looking at this is, our normal vector is 2 times 0, 3, negative 4. There. So you could have looked at the normal vector that way and said, oh, I'm not going to use 2 times this as my normal vector, just use a scalar multiple of the normal vector, which is all that really matters. You could have also switched the signs here on the 3 and negative 4, made it negative 3 and 4 and pulled out a negative 2 if you liked that better for some reason. Okay, so there's our answer here. Note again, you could have solved this as well for z and said this whole thing is z is, let's see, it'd be 5 minus y squared minus 3x squared over x cubed y. That would work out. And then you could use, when we had the, you could use the formula when we did the tangent plane to a function, f of xy, really the graph of a function was z equals some function of xy. But you'd have to take a partial of this with respect to x, partial this with respect to y, evaluate those points. That would work out okay. You just have to do a quotient rule a couple times, which I prefer to avoid. I feel like this is a lot more straightforward here. Okay, next one. This one's going to be short and sweet if we understand what's going on. So we have fxy is x squared minus 3xy plus y to the 5th. And we want to find the direction of the greatest increase of f at the point negative 2, 1. So what we're going to do is, what we're going to think about here is we're at the point, let's see, negative 2, 1. So we're here. This f of xy, I think what I tend to think of is maybe temperature here. So there's temperature at each point in the plane we have. And we're trying to figure out, do I go this way, like do I want to go sort of maybe that way, or that way, or that way, or what direction do I go from here to have the greatest increase in the function value, or maybe greatest increase in temperature? So that's really what we're trying to do. Now, the simplest way to do that is to recall that the direction of greatest increase is really in the direction of the gradient. So what we can do is we can just find the gradient of f. Again, that's vector of partial derivatives. So with respect to x, that's 2x minus 3y. With respect to y, that's minus 3x plus 5y to the fourth. And then we just want to evaluate that at the point we're at, negative 2, 1. Oops. And what you get is negative 4 minus 3, that's negative 7. And this is going to be, let's see, negative 3 times negative 2 is 6, plus 5 times 1, that's going to give me an 11. So in some sense, the direction I had is negative 7, 11. So it's going to be something like, more or less, like that kind of a direction. There should be the direction of greatest increase. Now, that's really all you need to know. Why does that work? Well, the directional derivative in a direction u of f, that again is u dotted with the gradient of f. And then when you have a dot product of two vectors, there's a general formula, a dot b is magnitude a times magnitude b times cosine of the angle between them. Well, what that means in terms of our directional derivative, we want to basically find the u that makes this directional derivative as big as possible. What we get is this is magnitude a, sorry, not magnitude a, letting u be a, so that's magnitude u, times the magnitude of the gradient of f, times cosine of the angle between u and the gradient of f. Now the magnitude of u is 1 if we let u be a unit vector. So I just get the magnitude of the gradient of f times cosine of theta. Now, for a particular point, gradient of f is going to be a fixed vector here. So this magnitude gradient of f, that's some positive number here. I guess it could be 0, but we're going to ignore that. So we're going to do some positive number. And what I'm trying to do is let cosine theta get as big as possible to make this whole value as big as possible. Well, this is maximized, so max when theta equals 0, that gives me cosine theta equals 1. But when theta equals 0, that means the angle between these two vectors is 0. That means they point in the same direction. It means they're a multiple of each other. So the direction of greatest increase is really in the direction of the gradient. If you want to find greatest decrease, you do the opposite direction of the gradient. Or direction of no change, you do a vector that's perpendicular to the gradient. Okay. Next one. Let f of xy equal x cubed plus y cubed minus 12x minus y. I'm going to find all local minima, local maxima, local minima, and saddle points for f. So first thing we're going to do is find our critical points here. And that's places where our partial derivatives are 0 or undefined. So our partial derivatives are going to be defined here because these are polynomials. And so I'm going to find, first step here is find our critical points. And so what I'm going to do is I'm going to take a partial f with respect to x. Here, and what I get is 3x squared minus 12. And then do a partial f with respect to y. And that's going to give me 3y squared minus 1. Now, what I need is both of these to equal 0 at the same time, or one of them to be undefined, but they're going to be defined for all x and y. So I'm going to just get a system, two equations here, two unknowns, but they're quadratic or can be uglier. Sometimes this takes some creativity to solve. In this case, it's not so bad. This first one, I can take this as 3x squared equals 12, which gives me x equals 4. Not x equals 4, x squared equals 4. Which gives me x is either plus or minus 2. Second equation here, this gives me 3y squared equals 1, which gives me y squared equals 1/3, which gives me, gives me y equals plus or minus about 1 over square root of 3. So we've got two values for x, two values for y. That really gives me 4 critical points. They are, I would write these typically as plus or minus 2, plus or minus 1 over square root of 3. But really this is 2, 1 over square root of 3, 2, negative 1 over square root of 3, negative 2, 1 over square root of 3, and then both negative. -2, -1 over square root of 3. So I have 4 critical points, and any local max, local min, or saddle point will occur at one of these critical points. So now to evaluate whether these are local mins, local maxes, or saddle points here, what I'm going to do is I'm going to find this Hessian or discriminant here. So I'm going to create a matrix here. Well, let me just say, the formula, well, I'll write it down the way I think of it, is it's a matrix of fx, let's see, it's fx, oh, sorry, no, sorry, it's partials. I'm getting confused here. So it's fxx, fxy, fyx, fyy, but note fxy and fyx are the same thing. So these are partials here. And I'm going to take the determinant of this matrix. So that's fxx, fyy minus, and I'm going to write this as fxy squared. Note again, fxy and fyx should be the same value. So this is what we're going to calculate. So to do that, fxx, that's a partial of f with respect to x, really taking a partial twice. So I take my partial f with respect to x, take another partial with respect to x, that's 6x. fyy is I'm going to take a partial with respect to y of the partial with respect to y, gives me 6y. And then the mixed partial is I can take a partial with respect to x and then take a derivative with respect to y, that gives me 0, or take the partial with respect to y, 3y squared minus 1, take a partial with respect to x, that'd give me 0 as well. You can do either order, they're the same. So in our case, what we get, whoops, is 6x times 6y minus 0 squared. This gives me 36xy. Okay. So what we get here, this is our discriminant. Now, what has to happen here is for a local min or local max, we need this discriminant to either be greater than 0 or I guess equal to 0, but then that's a sort of boundary case. We have to figure out something else to do. So what we get here essentially is that if 36xy is less than 0, our critical point is a saddle point. If 36xy is greater than 0, we could be, it's either a local min or a local max. And what's going to happen here, if you look at this, the way things set up is that if this is ever positive, because you're subtracting a square, that means fxx times fyy has to be positive, means either both fxx and fyy are positive or both fxx and fyy are negative, and those two cases are going to determine local min, local max. So let's see. Right away, our saddle points are when you take really x times y being less than 0, and for us that means really that we have a different coordinates for the x and y here, or different signs for the coordinates. So this is going to give us 2, -1 over square root of 3, and -2, 1 over square root of 3. So we get 2 saddle points. So those are saddle points. And then these other two could be mins or maxes. So what we're going to do here is that because we can just look at fxx. Let's see. Let's pick out the other point. How about I pick out a point? 2, 1 over square root of 3. fxx, well, that's 6x, that's positive. So that means in the x direction, the derivative is 0 at the point, but it's increasing. That means it has to go from negative to positive. That means it's going to look like this here. So that's going to be a local min in the x direction. And because fyy will have the same sign, if this whole discriminant is positive, or you just plug it in, I guess, you will get that they're both sort of local mins in that direction. So 2, 1 square root of 3, that's a local min. To me, I find it a lot easier just to sort of think through whether second derivative positive or negative gives me a local max or min each time than trying to memorize which way it goes here. And then the other point is -2, -1 over square root of 3, the other critical point. And there fxx, which is 6x, is negative. That means I have a 0, so I have a local min or max, or maybe a sort of a saddle point at when x equals -2 here. And so what I do is I'm saying, but then my derivative is 0, and my derivative is decreasing, that means it has to go from positive to negative, so it's going to be positive like this, and then decrease, so that's a local max. So -2, 1 over square root of 3, that's my local maximum. So we found 4 critical points, 1 local max, 1 local min, 2 saddle points. And this one means basically, when's the saddle point, means it's sort of a local min in the x direction, but a local max in the y direction, or vice versa. Okay, so in question 12, we have f of xy is y cubed plus 3x squared y minus 24xy plus 21y plus 1. And we want to find an absolute maximum and absolute minimum of f on a rectangle with these vertices. So first of all, let's draw our rectangle here. So what we've got, go down a little bit, let's see, 1, 2, 3, 4, 5 in the x direction. We need to go down 1, 2, 3, 4 in the y, and then up 2 in the y. And so our rectangle is going to have vertices. Let's just draw these here. Let's see, that should be, whoops, missed that one. 3, 2 should be there. 3, -4 should be there. 5, 2 should be something like that. 5, -4 like that. We've got a rectangle. Looks something like this. Here, really with sides where this is y equals 2. This is y equals -4. This side is x equals 5. This side is x equals 3. So there's our rectangle. And we want to find the absolute max and min on this rectangle. When we say on this rectangle, the intent here is to find the absolute value, not just sort of on the outside of the rectangle, but possibly on the inside as well. So to do this, what we're going to do is really the same thing we did in 11, looking for local mins and local maxes here. So we're going to find those first and then locate any local mins or maxes sort of on the rectangle. There may be some local mins, local maxes outside of the rectangle. We won't care about those. Here. So to find our local mins and maxes, we want to look where our partials are not defined. Well, this is a polynomial, so the partial derivatives will be defined everywhere. So we want to figure out points where both the partial with respect to x and the partial with respect to y are 0. So partial f with respect to x, that's 6xy minus 24y. And then partial f with respect to y will be 3y squared plus 3x squared minus 24x plus 21. And our goal is to set both of these equal to 0. So we want to find x and y that satisfy these two. Now, the first thing I would notice here is you can divide by a greatest common factor in both these equations. Just make them a little simpler. So the first one I can divide by 6, and I get xy, and it would be minus 4y, but I can write that 4y on the other side. So I get xy equals 4y. The second one I can divide everything by 3. So that's x squared plus y squared minus 8x plus 7 equals 0. Okay, now I'm going to focus on this first equation, the xy equals 4y. Maybe I didn't want to write the y on the other side, but one thing we could do, you have xy equals 4y, is you'd like to divide by y, but you can't do that if y equals 0. So if y equals 0, these two sides are equal or done. If y does not equal 0, you can then divide by y, and you get x equals 4. So we have sort of two cases, one when y is 0, one when x is 4. So what we're going to do is plug in, say, y equals 0 to this second equation and see what happens, and then plug in x equals 4 to the second equation and see what happens. So when we have the y equals 0, what we get is x squared plus 0 minus 8x plus 7 equals 0. And that will factor as x minus 7 times x minus 1 equals 0. So we get x equals 1 or 7. So that's when y equals 0, x is 1 or 7. So we get two critical points. 1, 0, no, not 1, 7. 1, 0, x is 1, y is 0, and then x is 7, y is 0. It turns out when we look at these, 1, 0 is like right here on our graph, 7, 0 is out here. Both of these are not on the rectangle or inside of the rectangle, so we don't care about those there. So those, they're local min or max of sort of the function viewed outside of the rectangle, but in terms of the rectangle, like they're sort of irrelevant. So y equals 0 didn't really give us anything that was useful. What about x equals 4? Well, if you plug x equals 4 into this second equation here, you get 16, so x squared is 16, y squared is y squared, minus 8x is 32, that's 8 times 4, plus 7 equals 0. 16 plus 7 is 23, minus 32 is negative 9. It's going to result in y squared equals 9. So we get y equals plus or minus 3. And that will give us 2 points. So x is 4, y is 3. X is 4, y is negative 3. Now if you look at your graph of this rectangle, 1, 2, 3, 4, if I go up to 3, that's outside of the rectangle. So we don't care about 4, 3. But for negative 3 is something like right here. That's really the critical point we want to be concerned about. Now, I could check this for a local min or local max or saddle point here. It's going to turn out that when I'm finding an absolute max or min, I don't really need to do that, because what I'm going to do is get local mins or maxes on these sort of edges or on the boundary. And then I'm just going to evaluate all of those, evaluate the original function, the y cubed plus 3x squared y minus 24xy plus 21y plus 1 at all of the various critical points we get here, either on the sort of end or on the edges here, or this one in the interior here. So I'm going to avoid checking if that's a max or min here, or at least I don't need to. Maybe one thing that would help, let's just do that for the sake of showing how you would do that, but it's totally unnecessary for this question. So maybe in red, here again, if I wanted to check if that was a local min or max, what I would do is take my discriminant, which is fxx, fxy, fyx, fyy, determinant of this matrix, that's fxx, fyy, minus fxy squared. Again, note fxy and fyx are equal, so you can just write those two multiplied together as pick one, I chose xy squared. Could have written fyx squared as well. And what I get, let's see, fxx, that's 6, this is our partial with respect to x here, 6xy minus 24y, so it's going to be 6x, and then the partial with respect to y, again, I'm going to get 6y and then nothing else. Oh, except I messed up my first one. So this isn't 6x. Partial with respect to x, that's 6y. So that's fxx. So I differentiate with respect to x, y is a constant. Then differentiate this one with respect to y. I get 6y there as well. Minus, I could take the first one and differentiate with respect to y. I already have x, and then differentiate with respect to y. It'll give me 6x minus 24 squared. And then you could plug in 4 for x and negative 3 for y. And what you would get is negative 18 times negative 18 minus 24 minus 0 squared. So this is going to be, well, in the end, 18 squared, which is greater than 0. That tells me this is a local min or local max. Because this fxx is negative, here what I'm going to get is a local max. Here. Now that doesn't tell me that's an absolute max, and again, all this stuff in red here is sort of unnecessary, because at the end I'm just going to evaluate a bunch of points. The original function had a bunch of points, including this one, and if another point has a higher function value, I'll use that one instead. Okay, so now we need to go through the context of trying to evaluate this function on these boundaries. So we've got 4 boundaries, sort of y equals 2, x equals 5, y equals negative 4, x equals 3. And what we're going to do is just plug in y equals 2 here and look for critical points as sort of a single variable calculus problem. So when you plug in y equals 2, I'm going to write down just f xy, what this was. That was y cubed plus 3x squared y minus 24xy plus, ugly, 24xy plus 21y plus 1. And we're first sort of edge, I'm going to pick y equals 2. You can do these in any order. So if y equals 2, I'm really looking at f of x comma 2 is, let's see, 8 plus 6x squared minus 48x plus 42 plus 1. And so this is 6x squared minus 48x plus a constant. I'm going to look for maxes and mins here. So I'm going to take the derivative, set that equal to 0. So I don't really care what the constant is, but 8 plus 42 is 50, plus 1, that's 51. Again, it doesn't really matter that this was 51 here. Okay, so I maybe could call this g of x, this f of x2. And I look at g prime of x would be 12x minus 48. And I want to set that equal to 0. And that's going to give me an x equals 4. So I can have, when y equals 2, I may get a local max or min at x equals 4. So what I'm going to do, it's going to be a 0.42. I'm just going to note up on sort of my chart here that, whoops, there's a point at 4,2. So we're sort of getting a catalog of points that we have to evaluate here. We're going to need the endpoints of each of these intervals. So we have the 4 corners of the rectangle, and we have 4, -3, and 4, 2. So maybe we should start making a chart off to the side. Let's see, we had 4, oops, hopefully there. Now let's go over here. 4, -3, 4, 2. Let's see, we also had our endpoints of, what is it, x equals 3, 2, and 3, -4, 3, 2, 3, -4, and the other vertices of the rectangle are 5, 2, and 5, -4. So far we're going to have to evaluate that function at these 6 points, but we've got 3 more sides to check here. So this is going to get a little bit tedious, but hopefully it's sort of straightforward at the same time. So y equals 2. The right edge of that rectangle was x equals 5. We're going to look at that, and here we'll just reuse g of x is f, x is 5, and plug in y. So this is going to be y cubed plus 75y minus 120y plus 21y plus 1. You put that all together, you get y cubed minus 24y plus 1. And we want to set that equal, well, not that equal to 0. We're going to set g prime of y equal to 0. I had a typo here, or maybe thinko. G of x, that shouldn't be g of x. This should be g of y. Y is our variable for this one. So g prime of y, and we want to set equal to 0, is going to be 3y squared minus 24 equal to 0. That will give me y squared equals 8. So y will be plus or minus square root 8. So x is 5, y is plus or minus square root 8. So square root 8 is going to be somewhere between 2 and 3. If you did 5 and positive square root 8, you would end up above and outside of the rectangle. But negative square root of 8 would be 1, 2, somewhere like here. So we're going to get a point, something like that, at 5 negative square root 8. So I'm just going to add that to my list. Okay, 2 more sides to check. The bottom of that rectangle is y equals -4. So here the function we're concerned about is like a g of x is f of x -4. And so that's going to give us a -64 plus 48y plus 96y minus 84, plugging in up here, plus 1. That's going to give me, let's see, 96y. Somehow I feel like I did not do this quite correctly. I shouldn't have a y here, so let's just redo this. We plug in -4 for y, and we get -64. For y, we're going to get minus 12x squared. I think I was plugging in -4 for x at this point, or maybe both x and y or something. Doing something wrong. -4 for y gives me a plus 96x minus 84 from the 21y, and then plus 1. So we get is -12x squared plus 96x. And let's see. And we get a 64 minus 84 is -20 plus 1. That's -19. Again, the constant doesn't really matter because I'm going to take g prime of x here, which is going to give me -24x plus 96. And I want to set that equal to 0 to find the critical point sort of along the line y equals -4. This is going to lend itself to x equals 4. So I get a point when x is 4, y is -4. Let's look at our rectangle. So our rectangle x is 4, y is negative 4. There's a point right there that's on the boundary. So we need to be concerned about that as well. Again, I could be checking all of these points that show up at the end for local min, local max. At the end of the day, I'm just going to evaluate the function of these points anyway, so it doesn't really matter. Last side here would be the left side, which was x equals 3. Left side of the rectangle. So we're going to get a g of y to be f of 3 comma y, which is going to be y cubed plus 27y minus 72y plus 21y plus 1. So let's say y cubed, let's see, 27, 48 minus 24y plus 1. If I look at this, I know this is the same g of y we had up when x equals 5. So there's maybe some symmetry about x equals 4 or something going on here. What that means in the end is I'm going to get y equals plus or minus square root of 8 again. You could run through this calculation again, but if you notice, hey, it's the same thing, you can just reuse that. And like before, positive square root of 8, when I'm up at x equals 3, I'm on this line here, when I get to positive square root of 8, that's outside of the rectangle, but negative square root of 8 is going to be in my, whoops, negative square root of 8. Let's undo that. So let's go here. I don't know what's going on here. Let's undo the... There we go. Okay, so negative square root of 8, that's going to be something like here. So those 2 points should be at the same height. In any case, what really matters is I get a point 3 negative square root of 8. Okay, so now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points I need to evaluate this function at. You could do those one by one. I'm going to try and use the calculator to be a little more efficient about this. So what I'm going to do here, I'm going to try and, let's just copy this. I'm going to go and see if I can copy all these points. Copy, go down to the next page, and I'll just list them out. Paste, well, then we've got to drag that down there. And let's go and find our function. Let's go ahead and copy that as well. Here, edit, copy, and then move down. I guess I'm going to put this here, and I need to do edit, paste. It looks like I lost one of my, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I lost part of that 1 point, didn't get in the copy. So 4, negative 4, 5, negative 4. Looks like the second to last one, that's the 4, negative 4. Didn't get copied appropriately here. So let's just 4, negative 4, add that in. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 points, and we want to evaluate them at our f of xy, this function down here. Now, I'm going to use the TI-84 here to do this, which illustrates some of the things that are a little bit problematic. Here's my general instinct when I'm trying to evaluate functions on here is to go to y equals and type in a function. That's not going to work very well here because I can only have one sort of independent variable. I can do a one variable function but not a two. I can kind of trick this into it though by going to stat, hitting the stat key. That will give me an edit which will get me to my list, and I can put in the x coordinates in L1 and the y coordinates in L2. So I have a 4, a 4, a 3, a 3, a 5, a 5, a 5, a 4, a 3, and then I'm going to put the y coordinates in L2 matching up the order. I'm going to do negative 3, 2, 2, negative 4, 2, negative 4, negative square root 8, negative 4, negative square root 8. I enter those in, and then in L3 I can kind of essentially put this function here. So y's, those are in L2. I'm going to do second. So what I have to do, let's see, I have to go highlight L3. So normally it starts out down here. Hit the up arrow, go up to L3, highlight that. And that second L2 to the third plus 3 times x squared. X is going to be L1 1 to the second times y is L2 minus 24 times L1 times L2 plus 21 times L2 and then plus 1. Hopefully this works. And this spits out all of our function values. And now what this means is that if you plug in 4, -3 here for x, 4 for negative x, 3 for negative y, you do f of 4, -3, you get 55. So my values here are, 55, -45, next one was -39, you get 33, -39, I get another 33, and then I get, let's see, 46.255, 46.255, and then 2 more. Probably a lot of these get repeated. 45, and then another 46.255. This is 45, 46.255. So my absolute max and absolute min have to be at one of these points. So at the end, my absolute max of, so the largest value, that's 55, and that was our interior critical point, it turns out, for -3. And then you have an absolute min, I was going to say at, I could do that first, but let's match what we did up here, of smallest value is -45 at the point 4, 2. So sometimes you really want the value, sometimes you really want the point. But those are 2 answers for absolute min, absolute max of this function restricted to the rectangle that we have. Now, pictorially, what's going on? Here, let's look at a graph of this function here. Let's blow this up a little bit more. Whoops. So here's the function. What you can see here is that there's sort of a very faint kind of curve here, and along sort of, I'm not sure which axis that is, but there's another curve here. So there's some sort of peak point in the middle here. That's going to be that 4, -3, that's our absolute max. And you can kind of see there's 50 on the z, 55 seems plausible. For 2, what that's going to be is that the min was down here in the bottom, and if you look at this, there's a really slight sort of slant up, kind of like a upwards facing parabola or something, so that min is somewhere in the middle. You'll note here, 4, 2, that's -45, 3, 2, and 5, 2, there's a -39, not too far off that value, which really is the same thing as saying this only goes up by 6, which is relatively not that big. Okay, so last question here. We have f of xy is 3x minus 2y plus z. We're going to find the maximum and minimum values of f subject to a constraint, x squared plus y squared plus z squared equals 14. So this technique here, when we're trying to find a max and min value of f subject to some constraint, generally, well, a technique that works is Lagrange multipliers. So when we have one constraint, the way this is going to look here is I'm going to let, first of all, oops, there's a typo here. When I look at this, I noticed that my constraint is xyz. F has xyz, but it just says f of xy. So that should be f of xyz. That didn't really work out too well. Let's get some more space here. So this should be f of xyz. So a small typo, but f is also a function of z here. So what we're going to do in this scenario is we're going to do gradient of f should be some lambda times gradient of g. So this is going to be, let's see, one equation. We're also going to have, x squared plus y squared plus z squared equals 14. I guess I didn't say what g was, so we're going to let g of xyz, so f is 3x minus 2y plus z, g of xyz is going to be this x squared plus y squared plus z squared. And so the idea here is we're going to do 2 level surfaces, or we're going to maximize a function, so constrained to some sort of level surface here. Basically, we're going to let level surfaces blow up here in certain directions, and that'll result in the gradients being perpendicular to each other. So there's some setup there. We'll talk about that later, but this is the general technique. Okay, so in our case, gradient of f, so this is really what we're looking for, not the one equation. Gradient of f, that is, let's see, 3 at partial with respect to x, partial with respect to y is -2, partial with respect to z is 1. Gradient of g is 2x, 2y, 2z here. And then we have this equation here. So if you'll note, you might be worried, well, there's x, y, and z are unknowns. Lambda is also an unknown. That's 4 unknowns and looks like 2 equations. But when you set these gradients equal to each other, you really get an equation from the x component, the y component, and the z component. So really what we get here is from the x component, we get 3 equals, no, we get a lambda times 2x. From the y component, we get -2 equals a lambda times 2y. From the z, we get 1 equals lambda times 2z. And then we get the x squared plus y squared plus z squared equals 14. So now we have 4 equations, 4 unknowns. This gets tricky to solve at times. I think what I'm going to do when I look at this is I'm going to solve for x, y, and z in each of these, plug into this. That'll let me solve for lambda here, and then I can go back up here and get those. So each of these I'm going to solve for, say, x. Looks like it's 3 over 2 lambda. Y looks like it's -1 over lambda. But not the best lambda there. Still not the best, but go with it. Z should be 1 over 2 lambda. And then I can plug these into this last equation. And so what I get is, let's see, x is 3 over 2 lambda squared, plus y is -1 over lambda squared, plus z is 1 over 2 lambda squared. This should be 14. So this is 9 over 4 lambda squared, plus 1 over lambda squared, plus 1 over 4 lambda squared equals 14. And let's see, we could multiply both sides by 4 lambda squared. So that will give us 9 plus, we have to multiply top and bottom by 4, plus 1 should equal 14 times 4 is 56 lambda squared. So that's 14 equals 56 lambda squared. 14 over 56 equals lambda squared. And notice the 56 was 14 times 4, and now I'm dividing by 14, or 14 factoring that out. Probably a little bit tricky, but I end up with 1 over 4 equals lambda squared. So lambda is plus or minus a half. So it could be lambda's positive a half or negative a half. Not sure which one we're going to do. So we really only have 2 options. So if lambda, let's just go up here. If lambda was, probably lambda equals a half, then we get x equals, let's see, well, lambda is a half, so x, this is going to be just x. The lambda and a half will cancel, so x will be 3. Y will be lambda times 2 is just 1, so y would be -2. And we get z equals 1. Same idea, lambda times 2 is 1. We get z equals 1. So we get that point 3, -2, 1. If lambda is -1/2, what we'll get is, let's see, -3, 2, and negative. Same thing as before, just with negatives. So it's going to turn out that if we have a max or a min subject to this constraint, it's going to occur either at 3, -2, 1, or at -3, 2, -1. So we have to go and find our function, 3x minus 2y plus z. Presumably one of those 2 points is going to give us the max, the other the min. So 3x minus 2y plus z. So this is f of 3, -2, 1. Well, let's just write that out again. So f, let's just clear space here. Let's do f of x, y, z was 3x minus 2y plus z. So f of the first point, 3, -2, 1, that's going to be 9, plus 4, plus 1, that's 13. Second point is -3 to -1. It's going to be -9 minus 4 minus 1. that's negative 13. So we get a max of 13 at the point 3, negative 2, 1, and a min of negative 13 at the point negative 3, 2, negative 1. And then we are done.